this on? Yes. Okay, so I was going to spend a significant amount of time working through a calculation in the adiabatic approximation, but I realized that I'm not leaving enough time to actually discuss the real self-force stuff at the end, so I'm going to try to just very briefly describe the adiabatic approximation. Before I get to that, let me clarify something I said yesterday about resonances. So remember I said that our theta resonances were intrinsic and our phi and theta phi were extrinsic, and that the intrinsic ones were more important. So the reason for that was, remember the equations for example, the equation for the orbital radius was a function just of r. The equation for the polar angle was a function just of theta. And the equation for t and phi only depended on r and theta. So this is a consequence of the symmetries of Kerr. The dynamics don't depend intrinsically on t and phi. T and phi are extra coordinates. The dynamics depend intrinsically on r and theta. And so as a consequence of this, not just these driving terms in the geodesic, but also the driving terms for the self-force, don't have any explicit dependence on t and phi. And so these ones, the extrinsic resonances, have a very suppressed effect, whereas the intrinsic ones have a very important effect. And what they actually do is introduce extra terms in long-term evolution of the phase. So remember I had psi alpha was 1 over epsilon, psi 0 alpha plus epsilon psi 1 alpha plus order epsilon squared corrections. As the orbit evolves, the frequencies will change with time, and you'll pass through resonances. These are transient resonances. You'll pass through, encounter a resonance, keep evolving out of the resonance, and that passage through resonance ends up introducing square root of epsilon term here. You can see has a major impact on the long-term evolution because it's multiplied by 1 over epsilon. So the total effect of resonance is a contribution 1 over square root of epsilon to the phase. So this is a very large effect. This is what happens if you pass through one major resonance over the course of a complete inspiral. If you pass through two, basically this whole thing gets messed up and we can't accurately approximate the evolution. Every passage through resonance essentially shifts terms by half an order. So if you have two resonances, then things that we're consistently neglecting will actually become important, like third order self-force effects. Okay, so that's all I wanted to say about resonances. Now let me talk about the adiabatic approximation. So this is basically the same adiabatic approximation that Luke described. The basic idea in orbits in Schwarzschild at least is that, say you have your big black hole, your small mass going around, gravitational waves go to infinity. This carries a flux of energy and angular momentum, which you can call E dot infinity and L dot infinity. And then you also have gravitational waves going into the black hole and getting absorbed by the black hole. And that creates a change in the black hole energy, which I'll call just H. So that's the flux of energy down through the horizon. And similarly, you have a L dot. And the basic idea is that this lost energy has to be coming from the kinetic energy of the particle. So if E0 and L0 are particles' energy and angular momentum, then you have balance laws, just saying that energy and angular momentum are conserved. So whatever left the system or whatever sunk into the black hole has to have come from E0 and L0, which means E dot 0 is minus E dot infinity minus E dot horizon. And similarly for L, and then what you do is you treat this as if it's moving on a geodesic. You calculate the fluxes of energy to infinity and down to the horizon and angular momentum. And then you use that change, using this balance law, to update the energy and angular momentum of the orbit, which puts you on a new geodesic. So you're slowly evolving from one geodesic to the next. Thank you. Now this balance law type picture only applies in Schwarzschild. So in Schwarzschild, a geodesic is labeled just by E and L. In Kerr, there are no balance laws like this. Or in particular, there's no balance law for the Carter constant, Q or C. So there's no notion of the flux of Carter constant in gravitational waves. So this simple kind of picture doesn't work for evolution in Kerr. And in that case, remember, at adiabatic order, all we needed was the first order dissipative self-force, but you do need to actually know what this is. You can't just rely on balance laws like this. So work beginning with Mino and later Sago et al. And Hughes et al. Showed how to calculate Q dot in a convenient way. So when I say convenient way, I mean in a way that only gives you this and doesn't require a complete calculation of the first order conservative force as well. And calculating this is much easier than calculating the conservative force. So there is a very useful numerical scheme for driving adiabatic evolution, where you go from one geodesic in Kerr to another geodesic in Kerr, and it's developed in papers by these authors. Now, I keep mentioning energy and angular momentum fluxes in the gravitational waves, and I keep mentioning that you're moving from geodesic to geodesic. How those things relate to the two timescale framework that I introduced last lecture might not be clear, so I'll say a couple things about that. So E dot and L dot in gravitational waves. In general, the flux of energy across the surface is minus integral over that surface, T alpha beta Z beta T actually let me call that S just to be consistent with these notes, ds alpha. So this is the flux of energy carried by matter. This is the outward directed surface element. So say we put a sphere here. What we're looking at is an integral over the sphere. And if you simplify this, you get minus T r squared d omega. So this is in Schwarzschild coordinates. And in Schwarzschild space-time. You'll have a similar formula in Kerr. Then the question is, well, let me write a similar expression for L dot. Here there's no minus sign, and you end up with T, well, I'll start with the covariant expression. So this is the time-like killing vector, this is the azimuthal killing vector. And simplifying this, we get there's a F here as well. The F was 1 minus 2m over r. And for L dot, you have r squared f again. And now it's t r phi rather than t t r. And integral over the sphere again. So these are just general expressions for how you define fluxes of energy and angular momentum across spheres in Schwarzschild, given some distribution of stress energy. Now the question is, what is T alpha beta for gravitational waves? So remember that in vacuum, we had delta G of H is minus delta squared G of H plus order H cubed. And just like Luke showed, you can think of this as an effective stress energy. So this is a nonlinear source that's driving a linear reaction. But let's get more specific. Recall that in the two timescale framework, again looking at, this is vacuum, so this is far away from the particle. So still in vacuum, what we had was this delta G alpha beta 0 K, where K labels the multiples of the phases, H 1 K equal to 0. So again, we're outside of the location of the particle. And at second order, we had a similar term for the second order perturbation, and then a term containing slow time derivatives of the first order perturbation, and that we can write as being sourced by this nonlinear piece of the Einstein tensor. So we're looking for the slow evolution, the adiabatic evolution of the system. And I said that this contains the slow time derivatives. The slow time derivatives tell you how things are evolving in a long time scale. And that slow evolution is being sourced by this. Remember, K here corresponds to e to the minus I K alpha psi alpha. These are rapidly oscillating things. But we want to look at just the slow evolution, which means we want to look at the K equals 0 piece. So the 1, 0. That's going to be constructed from the 1, 0 piece of the first order perturbation. So when K is 0, this oscillatory term disappears, and you're only looking at the slowly changing piece. And that means that is going to be sourced by the K equals 0 piece of this. So minus delta squared G alpha beta 0, 0. But that doesn't mean I put a 0 in here, because this is quadratic in H1. So I'll have combinations of these where the phases cancel each other. So this is slowly changing piece of the source. And it will be composed of things like e to the minus I k alpha psi alpha multiplied by e to the plus I k alpha psi alpha. So k, all the k's run over all ranges of integers, and so you can get these cancellations of phase. So it's just non-oscillatory now. So we want to pick off the non-oscillatory piece of this, which is constructed from combinations of oscillations in the first order field. So 8 pi T effective, so that's the effective energy of, or effective stress energy of gravitational wave, is this source here. So 0, 0, 1, k, which we can also write as just an average of this quantity. And I'll put a 0 here, meaning no slow time derivatives. So you take the quadratic combinations of H1 that appear in the source, and you average those over the fast time, just as in Luke's lecture. So that means this effective stress energy tensor is minus 1 over 8 pi times this. Okay, so this is how you would construct the fluxes. If you're doing an adiabatic evolution, you would calculate this and you can simplify it considerably. But I won't get into that in this lecture. And the second thing I mentioned was that I keep saying that the slow evolution drives you from geodesic to geodesic. But before I told you that in the timescale expansion, the leading order world line is not a geodesic. So remember, I had Z alpha is Z0 alpha. It's a function of slowly changing orbital parameters and these orbital phases. And since we're interested only in leading order for this adiabatic approximation, we can neglect the corrections. Oh, and one thing, yesterday I got a question about how is gamma related to Z? So gamma was just my notation for the world line of the particle. And Z are just the coordinates on that world line. Coordinates on gamma. Okay, then I said that the first order perturbation in the 2 timescale expansion is a sum over these phase factors with amplitudes here that are slowly changing with time. So this doesn't look like what you'd have for a geodesic because these are slowly changing with time, and these phase factors are the true phase factors on the accelerated orbit, not on geodesic. But these coefficients are identical functions, not of t tilde, but of J0. These are identical functions of J0 as what you'd have for the Fourier expansion for a series of H1 alpha beta sourced by a geodesic particle. So if you're just doing the Fourier series for a geodesic particle, what you have is H1 alpha beta J0 gamma, where these are not evolving with time. And what you'd have is the sum over integers, k gamma, where this would be a function of your coordinates are theta phi, but also a function of these orbital constants, times not the phase factor that you have for the accelerated orbit, but phase factor you have for a geodesic. So here, rather than psi, you just have omega t. But the point is, these coefficients are identical to these coefficients if you rewrite this t tilde as J0 of t tilde. This is what allows you to put your orbit, or put your particle on a geodesic, calculate the rates of change of E, L, and Q, and then use that to evolve to a new geodesic. It's because these coefficients are identical in the two setups. All right. So that's all I wanted to say about adiabatic approximation. I'm going to try to put together a fairly detailed exercise for you to do, just looking at an example of an adiabatic calculation. So that was what I was hoping to do on the board, but I want to move on to more with the actual cell force. So far I haven't said anything about the formula for the cell force, or how you calculate it, or how you derive the formula, or anything like that. So the rest of the lectures will focus on that. So before I move on, are there any questions about what I've covered so far? Nope. Oh, sure, thank you. So this lecture, the remainder of this lecture, and the next one are going to be on matched asymptotic expansions. And this is going to be a fairly different way of thinking about the problem compared to what we've been looking at so far. So far we've assumed that m, your small mass, can be treated as a point mass. So if you have a point mass, just like in Newtonian gravity or in basic electrodynamics, the field generated by that point mass is going to look like m over r. So note this is a change in notation here. R is distance from the particle, whereas before I had r as the Schwarzschild radial coordinate r. So that would be distance from the big mass. This is distance from the particle. So this diverges at the particle's position. So then the question is, what is the force exerted by H1 back on the mass? So because the field diverges at the particle's position, you'll have to extract some regular piece of that divergent quantity. You'll have to figure out what the regular piece is that exerts the actual physical force. So you would need to work out some regularization scheme and give it a physical justification. So what is the regular piece? Regular piece of H1 alpha beta that exerts the force. So that's not too bad a problem to have. There are lots of regularization schemes around. But at second order and higher order, the problem gets much worse. So the problem is much worse. So remember that I wrote down equations of this form. H1 was sourced by a point particle, and H2 was sourced by some correction to the point particle stress energy tensor minus delta squared G alpha beta H1. And remember, the form of this second order are things like the derivative of H1 squared plus H1 times second derivative of H1. So if we put in this point particle solution, then we have gradient of 1 over r all squared plus 1 over r times second derivative 1 over r. And so this derivative becomes 1 over r squared, and then you square it. So you've got m squared over r to the fourth. So this diverges very, very strongly at the particle's position. And when I say diverges very strongly, I mean something kind of strict in the mathematical sense. This is too singular. To be a well-defined distributional source. So normally when you're solving PDEs, if your source is singular, it's not too bad if you can interpret it as a distribution and still define integrals against it. So the solution will be some integral over the source. This source is too singular to do that. So say this is some small region that covers the particle, and we want to check if the integral of that source against a smooth test function, so this is just a test function, we want to see if this is well defined. So if R is capital R is small, we can always make it small by just making the support of the smooth test function as confined as we want it to be. Then we can replace this with its leading approximation there, which is m squared over r to the 4. And then we have phi and this r squared dr d omega dt. So this is smooth. We can just approximate this as its value at r equals 0 and pull it out of the integral. And what we've got is this r squared divided by r to the 4 gives us 1 over r squared. And these integrals over angles and t just come along for the ride, they're not important. And you see that this integral evaluates to limit as r goes to 0, m squared over r, which is infinite. This integral is not well defined, so the integral of the source against the test function is not a well-defined distributional operation. So to put it simply, this is not a good source. So if you tried to just put this into your numerics and tried to find the solution to the equation, you'd find that your solution never converges. No matter where you're trying to evaluate it, you can evaluate it infinitely far from the particle, you're going to get infinity as your answer every single time. So Luke may cover regularization schemes in the PN context. He's nodding, so I think he will cover that. So you can adopt some regularization schemes to get around that, around this kind of problem. That is not the approach that I'm going to cover. Oh, let me leave this up and go back to the other side. The approach I'm going to cover is matched asymptotic expansions. Now, to motivate the method, we'll just actually look at the physical problem that we're trying to solve. Actually, let me write one more thing about this, because this is a consequence of something very, very general in GR. This is a general result in GR due to Gauroche. The exact, by that I mean the fully nonlinear Einstein field equation with a point particle source has no solution within function space that's well behaved. So within a space of well behaved functions. So you will often hear people say that because of this, point particles are not well defined in GR, but it's probably better just to think of this as meaning exactly what it says and nothing more. So you can make use of point particles if you adopt a regularization scheme. It's just that if you look at the raw field equation without any regularization, you don't have a well-defined solution. But now physically, why is this? We have this picture, two black holes, and we've said that we were writing the exact metric of the full spacetime as the background metric of this big black hole plus small corrections. But if you look in a region very close to that small black hole, the gravitational field of the small black hole is not going to be much smaller than the gravitational field of the big black hole. It's going to be much bigger. So in this region, the small mass's gravity dominates. So it doesn't make physical sense to say that we're trying to approximate the exact metric as the background of the big black hole plus small perturbations, because these supposedly small perturbations are actually large if you're close enough to the small black hole. So the idea of matched asymptotic expansions is to introduce a different treatment of this region. So a different approximation. Now, before going into how we're doing it in GR, let me just look at Newtonian example. Let's say I have some large mass there. I have some small mass here, but the small mass has a mass distribution, rho. So the same kind of rho that Luke was describing. And let's say the distance between the two objects is capital R. not the same capital R I used there. And now in this Newtonian example, I want to look at the field in a small neighborhood around the smaller object. So this kind of small region. First, let me specify that the small object is compact. So assume M is compact, meaning that its size, we write the size as script R, that size is the same as its mass, or the same order as its mass in geometrical units. So it's not what you normally do in Newtonian physics, but let's go with it. Let's use Cartesian coordinates t, x, I, centered on the small object. So xi equals 0 will be inside the object. Then rho sources a Newtonian field that satisfies the Poisson equation. And I'll call that the S field, meaning the self field of the small object. So that is equal to 4 pi rho at distances that are large compared to the size of the object. So at distances r much, much larger than script r. So here r is distance from your small object. We know from basic Newtonian physics, or similarly from electrostatics, that we can write the solution to this equation in terms of multipole moments. Phi s is given by the mass over the distance from the particle, or from the mass distribution, plus a mass dipole moment term, plus a mass quadrupole moment term, where here Ni is a radial unit vector pointing away from the small object. We write that more like an N and less like an H. And this is 1 over r cubed. And similarly, you keep going up. In powers of 1 over r. Might be off by an m here. Definitely off by factors here, but I'll just absorb those into the definitions of the multipole moments. So these multipole moments are the moments of that matter distribution, moments of rho. So this is total mass contained in rho. This mi is the location of rho's center of mass relative to the origin of the coordinates at xi equals 0. And this is quadrupole moment of rho. So this is the general form of the object's gravitational field, or the small matter distribution's gravitational field, if you're not too close to the object. And it's characterized just by the object's multipole moments. At the same time, the large mass sources another gravitational field and because I'm interested in a region around the smaller object, I'm going to call this the external field, phi external. So it's what the small object perceives to be the external gravitational field. Near the small object, we can always expand this external field in a Taylor series. Around the origin of this coordinate system. And so on to higher orders. So over here we had an approximation that's good for R much larger than the size of the object, whereas this Taylor series is accurate for distances much smaller than the distance between the small object and the large object. So this external field is varying on this scale. So for these derivatives to be small, you need this relationship. But now we can combine these two results and look at a region that's far away from the small object relative to the size of the small object, but still close to the small object relative to the distance between the two masses. So use a different piece of chalk here. So this was valid, say, in a region like that. And we have a third color. And then this Taylor series oh wait, I've reversed them. So this is the Taylor series. And then, say out here, we use multipole expansion. But these regions will actually overlap. So what I want to look at is this intermediate region where both approximations are valid. So in this region, the total field, phi total, which is equal to phi s plus phi external, is the sum of these two expansions, m over r plus mi ni over r squared plus mij ni and j, higher order. And then we have the external field, evaluated at 0. And just to make the forms of the two more similar, I'm going to replace xi with r ni. So we have plus r phi external, evaluated at 0, times ni plus 1/2 r squared phi external second derivative, evaluated at 0, ni and j, and so forth. Now, I want you to keep in mind the form of this result, because even though we're going to be solving the nonlinear Einstein equations, this form will play a crucial role. So just keep this in mind. Okay, now let's move on to GR, away from Newtonian physics and into GR. Let me make use of the picture I've already got over there. Let me zoom in on this. We draw this a bit more to scale. A very small object. And I want to zoom in on this region around it. And we'll have r being the distance from this small object again. So out here, in most of the space-time, we use an expansion of the form that I already showed. I'll call this the outer expansion. Then in here, use a different expansion. Where the exact metric at leading order is going to be the metric of the small object rather than the metric of the large object. And that's going to depend on the distance, or of the ratio r over m. So think of, if this is a Schwarzschild black hole, you know that the field around it depends on m over r, or r over m. M sets the scale in this region. And now we're going to have corrections, which I'll write as a capital H rather than a lowercase h. And again, these are going to depend on r over m. You might be wondering, what exactly do I mean by r there, because you can have different definitions of distance. What I'm about to say is going to be valid for most choices, pretty much all. But then later on, in tomorrow's lecture, I'll choose a particular coordinate system that will define what that little r means. Okay, so concretely, adopt some coordinates that are kind of Cartesian in form, t, x, a, again centered on the small object. And now let's define scaled distances, or scaled coordinates, that I'll call x bar a, which are xa over epsilon. So it's basically what I've written here. Remember that epsilon is just counting powers of little m. Now in these coordinates, the outer expansion is an expansion in the limit epsilon goes to 0 at fixed xa. So thinking kind of physically, that means that xa is of order epsilon to the 0. It's an order 1 quantity that we're not sending to 0. Or we can also think of that as being the scale of the big black hole. And then this expansion over there will have a form like this. So on to higher order. So it's just a series in epsilon. The inner expansion, did I label this? So, yeah, so this over here is the inner expansion. So this is an expansion for small epsilon at fixed scaled distances. So at fixed x bar a. So thinking kind of physically, that means that x bar a is of order 1, order epsilon to the 0, which means xa is of order epsilon, or you can think of that as being of order the small mass. So you can think of this inner expansion as kind of zooming in on the small object, on that small region around the small object. So to illustrate that, I'll just draw a couple plots. So first, let's look at epsilon, the epsilon r plane. So this r is just the square root of x squared plus y squared plus z squared, which I can write as delta ij x I x j. So these two different limits that I'm looking at look very different on this plane. So the outer expansion, I'm taking epsilon goes to 0 at fixed xa, which means fixed r. So those are curves like this. So that's the outer expansion, where the outer expansion is an approximation as you take that limit down to the bottom of the plot. And the inner expansion is at fixed x over epsilon, which means it's going to be going down towards the origin of this plane like that. So that's the inner expansion. So you can think of this expansion or this limit as following the object as the object shrinks down towards 0 size as epsilon goes towards 0. You can also draw the same picture in the epsilon r bar plane, which was r over epsilon. So in this case, the inner expansion is epsilon goes to 0 at fixed r bar. So that's curves going straight down in this plane. It's the inner expansion. The outer expansion is then going out like that. So the inner expansion is keeping the size of the object fixed. So the object is some fixed size on this picture, keeping the size of the object fixed, but sending all other distances out towards infinity. So you still have the case that the object is much smaller than the external distances, but in the inner expansion, rather than letting the size of the object shrink down to 0, you're letting the external distances grow up to infinity. Whereas the outer expansion, you're keeping the external distances fixed, like the distance from the small object to the big black hole, but you're letting the small object shrink down towards 0 size. So that's the physical picture of these two different limits. Now, one small technical note. Wait, I didn't write down actually this, but it should be fairly clear. Just all the coefficients depend on the scaled distance. And so on to higher order. The technical note was, remember I discussed the 3 different ways of incorporating evolution into the Einstein equation or into the metric perturbation. And so if you're using a Gralla-Wald case where you're just doing a Taylor series expansion of all your quantities, then you get expansions like this, where all the coefficients, g, h1, h2, g object, capital H1, capital H2, they don't have any dependence on epsilon. If you're using the self-consistent expansion, which I will use just because it gives simpler looking equations of motion at the end, then all these coefficients depend on gamma, which is the world line of the small object. Now, the last thing I'll say today is really the key to this whole approach. We have 2 expansions, and the name of the method is matched asymptotic expansions. So the key idea is that these 2 expansions have to match each other. So we have a matching condition. So the expansion, the outer expansion, and the inner expansion are both expansions of the same exact metric. Yep. The first one. So really what it is ultimately is the large mass itself. So when we're looking at emeries, the distance between the large mass and the small companion is of order the size of the large mass. So that's a big difference between post-Newtonian theory and emeries. In post-Newtonian theory, the distance between the two objects is much larger than either of the masses, whereas for us, the large mass sets the overall scale. So that's why here I've said that epsilon to the 0 is of order capital M. Capital M is, you can think of as just being the overall scale, so it's an order 1 quantity. So the large mass is comparable to the orbital separation. Okay, so these are two expansions of the same metric. Expansions of same metric. So they must match each other. Now, I don't have time to actually tell you the mathematical meaning of the statement, but this is the key physical idea that I will then explore in tomorrow's lecture. Right? Thanks.
We have time for a couple of questions.
You mentioned that the coordinates that are centering on m, small m, are somehow Cartesian in
Pseudo-Cartesian, yeah.
All right. But how you build those coordinates are similar to Riemann or Fermi coordinates in
Fermi,
some sense?
yeah.
Okay.
So they are exactly Fermi coordinates. So I'll review or introduce Fermi coordinates tomorrow.
Oh, okay. Thank you.
Fermi Walker coordinates rather than Fermi normal coordinates. Slightly different.
Because it's rotating or something?
Because it's accelerating.
Ah, okay.
Okay. So we now go for lunch. So be sure you're back by 2 sharp.